So let us begin with the new chapter, chemical bonding and molecular structure. So in this chapter we will study about different kind of chemical bonds and the structure of the molecules. So let's define chemical bond. It's an interatomic attraction that holds two atoms together. It's quite straightforward. So what is the cause of chemical bonding? Why two atoms will come close together? The reason is the tendency to acquire stability. So more stable the state is, that is the state of minimum energy. So that's a natural law that any system tries to get into a state of minimum energy. Second, tendency to acquire noble gas configuration. So we already studied that briefly before, that noble gases are the most stable, they have the most stable configuration. So the elements which are before and after noble gases in periodic table, they try to release or catch electrons to form the noble gas configuration. So what is the noble gas configuration? Typically it is NS2 NP6. The only exception is helium, which just has 1s2. But otherwise all the noble gases have their valence shell configuration of NS2 NP6. That is 8 electrons in their valence shell. Valence simply means the last shell. So this 8 electrons is also called as octet rule. So all the atoms will try to get 8 electrons in their valence shell and thus follow the octet rule. So this approach of trying the atoms which try to get 8 electrons in their valence shell, so this approach is also known as Cossell and Lewis approach. Let's formally define octet rule. So noble gases except helium have valence shell configuration of NS2 NP6. Octet rule states that an atom will gain, lose or share electrons to acquire a stable configuration of 8 electrons in valence shell, which is similar to noble gases. So there are some notes regarding the octet rule. First is inner shell electrons don't participate. So we are only talking about the valence shell electrons. So only valence shell electrons will try to get 8 electrons in its orbits. Electrons present in outermost shell, which is valence shell of an atom, are called valence electrons. Lewis symbol. So this is just a nomenclature where you draw the symbol, you write the symbol of the atom, and then you mark the number of valence electrons on that particular atom. So in case of hydrogen it is 1, for helium it is 2, for lithium it is again 1, for beryllium it is 2, for boron it's 3, like that. So this is the except hydrogen and helium, these belong to the second period and they are quite important. So at least the fluorine, oxygen, nitrogen, carbon. So you should know that these atoms, how many valence electrons they have. So that will help you understand how the molecules are formed from these atoms later on. So let's dive directly into the first kind of bond, which is ionic bond. So when electronegativity difference of two atoms, we already studied about electronegativity in previous chapter. So when the difference in electronegativity is large, example sodium and chlorine. So one with the more electronegativity, chlorine, will gain the electron from the electropositive atom. In this case it is sodium. So electronegativity is the tendency to attract the electron. So the more electronegativity chlorine has, the very less electronegativity sodium has. So when these two atoms come together, sodium will donate its electron to chlorine. So it's also called the gain of electron by chlorine. So to achieve the nearest noble gas configuration, both Na and Cl by this process will achieve the nearest noble gas configuration. So let's see that. So sodium has atomic number 11. So let's write the configuration. It is 1s2, 2s2, 2p6, 3s1. So you can see that it has one valence electron in its valence shell. So valence shell is the last shell of an atom. So here 3, it is a valence shell is 3 and it has only one electron. For chlorine, Z is equal to 70. and its configuration is 1s2, 2s2, 2p6, 3s2, 3p5. So again 3 is the valence shell, and how many electrons this valence shell has? 2 plus 5, which is 7. Now nearest noble gas to sodium, it is 1s2, 2s2, 2p6 neon, and to chlorine it is 1s2, 2s2, 2p6, 3s2, 3p6. So you can see that if sodium loses this electron, then it will achieve the nearest noble gas configuration. And chlorine, if it gains one electron, if this becomes 3p6, then it achieves the configuration of argon, which is the nearest noble gas to chlorine. So this happens, sodium will give its electron to chlorine. So from 281 and 287, both will become 28 and 288, which is the noble gas configuration for both the atoms. So this is the ionic bond which forms between the two ions, and they are held together now by electrostatic force of attraction, since they have charges on top of them. So every ionic bond will have a cation, it is the atom which will lose the electron, and an ion which gains the electron. Some more examples of ionic bonds. CaCl2. So calcium has 2 valence electrons, and chlorine, we already saw, has 7 valence electrons each. So calcium will donate both of its valence electrons to chlorine. Charge on the calcium will become +2, on both the Cl it will become -1, and you will see that all three have now achieved a noble gas configuration. Li2O. So Li has single electron in the valence shell, oxygen has 6. So to achieve a noble gas configuration, oxygen needs 2. So it will take 1 electron from this lithium and 1 from this, and therefore will form a molecule of Li2O, MgO. Here Mg has 2 extra electrons and oxygen has 2 less electrons. So magnesium will give both the electrons to oxygen and it will form MgO, MgF2. Now again Mg has 2, but fluorine only needs 1. So 2 fluorine atoms will take 1 each from magnesium and it will become MgF2. Calcium oxide, calcium has 2, oxygen has 6. So oxygen will take both to become CaO. Na2S, so Na has 1, sulfur has 6. So sulfur will take 2 electrons from 2 Na atoms and become Na2S. So this is the example of octet rule and how these reactions are taking place in order to follow that octet rule and trying to achieve a noble gas configuration. So in all these cases, you'll see that all the atoms have now a noble gas configuration. Electrovalency. It is the number of electrons an atom gains or loses during formation of ionic bond. So we have seen the examples already, but let's go back to those examples and see what is the electrovalency of the atoms. So in this case, calcium is losing 2 electrons, so electrovalency of calcium is 2, of chlorine 1, of oxygen 2, of magnesium 2, of oxygen again 2, of fluorine 1, of magnesium 2, of calcium 2, oxygen 2, sodium 1, sulfur 2. So number of electrons, it is either gaining or losing. So each of these atoms, you can see the electrovalency is either 1 or 2. There are examples of electrovalency of 3 also that we'll see now. So in the first group, all the atoms which are in the first group of periodic table, they have electrovalency of 1. So all of them will try to lose 1 electron each. Of the second group, the electrovalency is 2. So all of these atoms will form a cation of charge +2. Aluminium +3. So aluminium would rather lose 3 electrons to achieve the noble gas configuration of neon. And fluorine here, for example, will gain 1 electron to form the neon noble gas configuration. So it goes like this. So it nitrogen, oxygen, fluorine, neon, then sodium, magnesium, aluminium. So they have 1 extra electron, more extra electrons than neon. So if these elements, they lose electrons, they will form neon. And if these elements which are falling before neon, if they gain electrons, then they will have the valence shell configuration of neon. Again, in the case of argon, so if chlorine gains one electron, it will have the valence shell configuration of argon, and potassium, if it loses one electron, then again it will have the valence shell configuration of argon. So these are the electrovalencies which are written here of the more popular of the elements. So it's good to remember all these except perhaps the strontium. So from table you can see that Li and F, they have +1 and -1. So when these two react together, it will form LiF, Be and F. So beryllium has +2 and F is -1. So these two will react and form BeF2. Calcium and oxygen. So calcium is +2, oxygen is -2. So they will react to form CaO. Sodium and oxygen. Sodium is +1, oxygen is -2. So it will become Na2O. So this gives you certain idea of how these elements will react among themselves to form ionic bonds. So what will be the ratio of the number of atoms of these is to this. Variable electrovalency. So till now we saw that the electrovalency was just a static thing, but it does not always happen like that. So sometimes electrovalency is variable. So in previous chapters we already saw that copper and iron, they have variable valencies. So how and why it is like that? So the reason is unstable core. So once the electron is released from, let's say, Fe, and 2 electrons, so okay, let's take an example of iron to understand how the variable electrovalency works. So configuration of iron is 1s2, 2s2, 2p6, 3s2, 3p6, 3d6 and 4s2. So from here you can think that iron should have the electrovalency of only 2. So if it loses these 2 electrons, it will have the configuration of 3s2, 3p6, which is of the noble gas. But in reality, what happens is when it loses these 2 electrons, this becomes 1s2, 2s2, 2p6, 3s2, 3p6 and 3d5, 3d6. So when it loses these 2 electrons, it will achieve the configuration of 3d6. How the 3d6 looks like? This. And we already know that half-filled orbitals of a particular subshell are more stable. So this electron is actually making it quite unstable. So it can lose one more electron quite easily, and then it can form a configuration of 3d5. So then it will have the d orbital, which is exactly half-filled. D subshell, which is exactly half-filled. So each of the orbitals of d shell will be half-filled, which is more stable than this. So the iron, it has a electrovalency of 2 and 3 both. Sometimes it reacts with the electrovalency of 2, sometimes it reacts with the electrovalency of 3. So the reason is unstable core. So this core, which is left after losing the 2 electrons, is still unstable because of this extra electron. So it will try to stabilize more by losing one more electron, and therefore it will have one more electrovalency, which is +3. The second reason is, or the second reason of having the variable valency is inert pair electron effect. It is the reluctance of ns2 electron pair to take part in bond formation. Let's learn that from an example. So strontium, it has a configuration of 1s2, 2s2, 2p6, 3s2, 3p6, 3d10, 4s2, 4p6, 4d10 and 5s2 and 5p2. So it has a reluctance to lose these 2 electrons. Ideally, it should lose all 4 to form a noble gas configuration of 4s2, 4p6. But it is reluctant to lose this 5s2. So it will lose these 2 first. So it will have a electrovalency of +2, and then it will lose 2 more to have electrovalency of +4. So inert pair electron effect. The reason is ns2 electron pairs reluctance to take part in the bond formation. So 5s2 will try to retain itself. So once the 2 electrons of P are gone, that is more stable than plus 4. So it shows the valency of electrovalency of plus 2 and plus 4. Factors helping ionic bond. So we see that the two atoms which are participating in an ionic bond, so what are the factors that help? Low ionization energy of electropositive atom. Ionization energy is a measure of how difficult it is for an electron to be removed. So ionization, for example, uh, for the noble gases, taking out an electron is very difficult, so it will have high ionization energy. So ionization energy is the energy which is given to an atom to remove its electron. So electropositive atom, so for example sodium, that should have low ionization energy, so it should be easier for electropositive atom to lose the electron. So low ionization energy. Second, more negative electron gain enthalpy of electronegative atom. So if you remember, the electron gain enthalpy is quite the opposite of ionization energy. So more ionization energy means difficult to lose the electron, and here the more negative electron gain enthalpy means it's easier to attract an electron. So more negative should be of the electronegative atom. So the more negative it is, it's easier for the electronegative atom to accept the electron from electropositive atom. Third, lattice energy. It's the liberation of energy when the compound formed condenses. So what happens is when the ionic bond is formed, so that it might be like a liquid or in a gaseous state, but eventually when it condenses and forms crystals, some energy is released. So if the higher the energy is released, that means it is more stable, and therefore it will be easier to form the ionic bond. High difference in electronegativities. This point is same as combination of 1 and 2. If the electronegativity difference between the two is more, that means one has huge tendency to attract the electron and other one has very less tendency to attract the electron. So the one which has more tendency will just take the electron from the one which has less tendency. Let's talk about some properties of ionic compounds. First, physical state. So they form crystalline solids. So simplest example is common salt, which is NaCl. So you can see that this is the structure of their lattice, and if the smaller one, this is the sodium, and the bigger atom is the chlorine. So each atom of sodium is surrounded by 6 atoms of chlorine. So these are the crystalline solids. So physical state, crystalline solids. High melting and boiling points. So certainly, since it's fixed in a lattice like this, it's very difficult to break all these bonds. Hard and brittle. So it is hard because the electrostatic force is very high between Na plus and Cl minus. So it is like Na plus, Cl minus, so Cl minus, and this Na plus is surrounded by again Cl minus. So this is not a ionic bond, but it's a force of attraction, and it is surrounded by these kind of Cl minuses. So these all electrostatic forces of attraction make the lattice very hard. Brittle. So as you can see here, that plus is this Na plus is attracted to Cl minus, and it will be like Na plus here and Cl minus here, and this is the structure of your lattice. So a positive cation is surrounded by negative cation. So if this is the structure, so you can this plus you can assume as sodium and negative as chlorine. So this is the structure of your lattice. So it's brittle because when, let's say, some shear force is applied, so if this layer moves here and this layer moves here, you'll see that these negative ions will come together, this plus will come together, and because of this, the force of repulsion will just break this crystal apart into two pieces. So that's why they are brittle. Finally, they are soluble in water. So H2O, water itself, is kind of dielectric, it's polarized. So these ions Na plus and Cl minus, they will disassociate themselves once they are inside the water. So ionic compounds are soluble in water. Let's start with covalent bond now. So when two atoms having similar or almost similar electronegativities can achieve a stable valence shell configuration, 2 or 8 electrons in outermost shell, by sharing of electrons between them, then that bond is covalent bond. So till now we studied that one atom gives the electron and other atom accepts it. But here it's about sharing of electrons. So let's understand that with an example. So let's take the two hydrogen atoms. Both of them have one valence electron each. So this one electron is being shared by both, and the other electron of hydrogen is also shared by both. So both of the hydrogen atoms have kind of your noble gas configuration now, so by having these two shared electrons. So this is called a shared electron pair, and it's represented by just H-H. For chlorine, chlorine has 7 valence electrons. So two chlorines will share 1 electron each. So both will have 8 electrons. NH3 and nitrogen has 5 valence electrons. It is when it is surrounded by 3 hydrogen atoms. So each of these hydrogen atoms will share its 1 electron with 1 electron of nitrogen. So you will see that nitrogen now has 8 and each of the hydrogen has now 2. So again the octet is still followed and all the atoms have now noble gas configuration. So more examples: water, H2O. So you can just go through it quickly. Okay, let me just. So oxygen has 6. So one of oxygen will be shared with one of hydrogen, and one of oxygen here will be shared by again one of hydrogen. So oxygen will have 8 and hydrogen will have 2 each. Carbon has 4. So with the hydrogen, again carbon will have 8 and each of the hydrogen will have 2. PCl3, phosphorus has 5, 3 chlorine. So one here, one here, one here. Again chlorine will also have 8, phosphorus will also have 8. Oxygen. Now in case of oxygen has only 6 electrons. So if it shares only 1 electron with the other oxygen, it will have only 7 valence electrons. So instead of sharing just 1, it shares 2 electrons. So now these 4 electrons are shared by both. So each of them now again have 8 electrons. So this is a case of multiple covalent bond. Same with the case of nitrogen. Nitrogen has only 5 valence electrons. So two nitrogen atoms need to share 3 and 3 each to form a 8 electron configuration. So this is a triple bond. This is a double bond. C2H4. So carbon has 4, hydrogen has 1. So this is an example where you have a single covalent bond and double covalent bond both. So again carbon will have 8. C2H2. So carbon and carbon will share 3 each and carbon and hydrogen will share 1 each. So again this is a case of multiple covalent bond and a triple bond. Factors favoring covalent bond: high ionization energy. That means it's easy to share an electron, because if the ionization energy was low, then it will have a tendency to donate an electron. High ionization energy means the atom is reluctant to give away its electron, but it is acceptable for an atom to share it. Equal electron gain enthalpy. So it has to be equal, the tendency to attract an electron. Otherwise, if one has more tendency to attract the electron, it will just take the electron from other atom. Similarly, equal electronegativities. Number of valence electrons should be preferably 5, 6 or 7. So obviously if it has lower number of valence electrons, then that atom has a tendency to give away its electron rather than sharing. So only when the valence electrons are nearer to 8, then it will have a tendency to share the electrons. High nuclear charge and small interatomic distance. Let's take an example of two atoms here which are sharing this electron pair. Now sharing of electron pair is fine, but why these two are stuck together? It's because of the force of attraction between this nucleus and this electron cloud, and this nucleus and this electron cloud again. So this attraction force between the nucleus and the electron cloud, it's more if the nuclear charge is more, and if the distance, interatomic distance, is less. In both these cases, the attraction force will be more, and these two molecules will have, these two atoms will have more tendency to form a covalent bond. Covalency. So let's take an example first before we get into the definition. So for chlorine it's 1, for oxygen it's 2, for hydrogen it's 1. This is the number of valence electrons shared by an atom to form covalent bond. Pretty straightforward. Again, variable covalency. So for example, sulfur, it has Z16. So let's draw it. It is, so there will be 1s2, 2s2 and 2p6. After that it will be 3s2 and 3p4. So it will be filled like this. So it has variable covalency, because right now you can see it has a covalency of 2. But sometimes this electron will jump into the 3d orbital, so this will become a more stable half-filled state. So it's called the first excited state, because this electron is jumping into the next orbital. So in this case the covalency is 4. Again, when the more excitation energy is given, this electron will also jump to the 3d orbital. Now the covalency of sulfur will be 1, 2, 3, 4, 5, 6, 6. So sulfur shows a variable covalency of 2, 4 and 6. So among these three, 6 is called the maximum covalency. Characteristics of covalent compounds. So low melting and boiling points. Since their intermolecular forces are usually weak, they can be overcome by little amount of heat. Why they are weak? Because compared to ionic compounds which have a positive and negative charge, net positive and negative charge, so that force is much more stronger, attraction force is much more stronger than just the force between the nucleus and the electron cloud. Solubility, so they are generally insoluble in water. Parameters of covalent bond. Bond energy. So it is the amount of energy required to break 1 mole of bonds to separate the bonded atoms. So for example, you have a HF, 1 mole of HF molecules. So the amount of energy required to break all those HF bonds of 1 mole. So that energy will be called as bond energy. So amount of energy required to break 1 mole of bonds to separate the bonded atoms. So it depends on two factors. If the atoms are smaller, that means more energy is needed to break them. So needless to say, if they are smaller, that means they are closer to each other, stronger bonds. And if there are multiple bonds, then also there will be more energy is needed to break them. So HF, fluorine is smaller than chlorine. So HF bond is much stronger than HCl. So more energy is needed to break HF bond. Therefore, more bond energy is, therefore HF will have more bond energy. Now, C can be attached with the oxygen in a double bond or a single bond. So if it is a double bond, then that bond is stronger than a single bond, and obviously more energy is needed to break that. So bond energy of a double bond is more than bond energy of single bond. Bond length, it's the average distance between nuclei. So if the average distance between nuclei is smaller, the bond is stronger, and that's the reason they both will follow the same thing. So if the smaller atom, that means less bond length, and multiple bonds also means less bond length. Third, bond angle. So it's quite straightforward. So in a case of water, for example, HO and H, this is the angle between HOH, which is 104.5 degree. So bond angle of HOH is, water is 104.5 degree. Formal charge. So it's defined, it's just a definition. It doesn't have any physical significance, but we define it as, for atom in polyatomic ions and molecules, it is defined as total valence electrons minus total lone pair electrons minus half of total shared electrons. So what are lone pair electrons? We know what are valence electrons for an atom. So the lone pair electrons are the electrons which are not combining with anything. Total shared electrons are the electrons which are shared between the two atoms. So let's take an example of ozone. So it has a double bond here and a single bond here. So double bond means these four are shared. Single bond means only two are shared. So this blue dots are the shared electrons, green dots are the lone pairs. So oxygen has 6 valence electrons. So these four for this molecule 1, 2 and 3 are actually, this is contributing both of its electron to this oxygen. So it is 1, 2, 3, 4, 5, 6. For this oxygen molecule 1, 2, 3, 4, 5, 6. For this oxygen molecule all 6 are not used in the bond formation. So let's calculate the formal charge. In first case, it is total valence electrons, which is 6. For all 3 oxygen molecule atoms, total valence electrons are 6. 6 minus total lone pair electrons, so it's only 1. So there is only one lone pair. So lone pair electrons are 2. 6 minus 2 minus half of total shared electrons. So with the oxygen atom, how many shared electrons are there? 4 plus 2, which is 6, minus half times 6. So it comes out to be plus 1. For second atom, the valence electrons are again 6, minus total lone pair electrons 1, 2, 3, 4, minus 4, minus half times shared electrons. So minus half times 4. So comes out to be 0. For third atom, valence electrons are again 6, minus number of lone pair electrons 1, 2, 3, 4, 5, 6, minus half the number of shared electrons. So number of shared electrons is 2, half of it will be 1. So 6 minus 6 minus 1 comes out to be minus 1. So this will be the Lewis structure of your ozone molecule. So that's the end of this part. We'll continue chemical bonding in the next lecture.